The James Webb Space Telescope, a pioneering piece of space technology, represents a significant leap forward in our capacity to explore the cosmos. Developed through an international collaboration led by NASA, with substantial contributions from the European Space Agency and the Canadian Space Agency, the JWST is designed to complement and surpass the capabilities of its predecessor, the Hubble Space Telescope. With its primary mirror spanning 6.5 meters in diameter, the JWST has a light-collecting area more than 6 times that of Hubble, allowing it to peer deeper into the universe than ever before. One of the key instruments on board the JWST is the mid-infrared instrument. This high-resolution device is incredibly sensitive to infrared radiation, enabling it to detect faint heat signatures from distant celestial objects. MIRI's capabilities are crucial for observing exoplanets, distant galaxies, and other astronomical phenomena that emit primarily in the infrared spectrum. The instrument's precision makes it possible to detect subtle variations in light and heat, opening new avenues for understanding the formation and evolution of planets, stars, and galaxies. Observations of Proxima B, one of JWST's most amazing achievements, is the artificial light observation of Proxima B, an exoplanet orbiting Proxima Centauri. The discovery is the first real evidence of a technosignature, a signal of advanced technology on another planet. Just over 4 light-years from Earth, Proxima B is in its parent star's habitable zone, meaning it could potentially support liquid water, and thus life. The detection of artificial light suggests that Proxima B may contain intelligent life forms. This conclusion is based on the fact that artificial light, such as that of cities and industrial plants, probably does not occur in nature. MIRI's ability to distinguish between natural and artificial light sources allows scientists to make these amazing discoveries. By analyzing the beacons of Proxima B, scientists can infer the presence of large cities or large industrial complexes, indicating the presence of an advanced civilization. Technical news and future telescopes. The capabilities demonstrated by JWST are just the beginning of what future telescopes can achieve. In 2028, the Very Large Telescope, ELT, is scheduled to be commissioned in Chile. With a primary mirror 39 meters in diameter, the ELT surpasses all previous telescopes in light gathering and fine detail resolution. This huge aperture allows the ELT to look deeper and sharper into space than ever before, providing an unprecedented view of the universe. The high-resolution capabilities of the ELT are particularly valuable for exoplanet research. By analyzing the light from these distant worlds, the ELT can determine the composition of their atmospheres, surface conditions, and potential for life. The combination of JWST and ELT represents a powerful duo that seeks to understand our place in the universe. These technological innovations are essential as our thirst for space knowledge remains unquenchable. In addition to these advances, the aerial extinction recovery system is another promising tool for the search for extraterrestrial life. This system is designed to detect traces of vegetation on distant planets by analyzing specific wavelengths of light reflected by plants. Such developments highlight the continued progress in the search for other species in space. A quantum leap. The observation of the artificial light from Proxima B is an important leap in the search for extraterrestrial life. This discovery indicates the presence of technology on the planet, indicating that its inhabitants have reached a level of development equal to or higher than ours. The implications of this discovery are profound because it not only suggests the existence of life beyond the Earth, but also suggests the possibility of communication with those distant civilizations. JWST's ability to analyze our own activity on Earth based on light signatures underscores it. Impressive capabilities. Major cities such as New York, Rio de Janeiro, and Beijing, as well as airports, industrial facilities, and space stations, produce distinctive beacons that can be observed from space. By applying the same principles to Proxima B, scientists can gain insight into the level of mechanization and technological development of its inhabitants. Interacting with Proxima B presents significant challenges, however. Given the enormous distance between our solar system and Proxima Centauri, it would take more than 4 years for messages to reach the planet. Returning each answer would take another 4 years, respectively. Current hopes are focused on the development of quantum communication technologies that would enable real-time communication with distant civilizations. Fully realized, quantum computers could transform the way we communicate across great distances, turning what seems like pure utopia today into a tangible reality in the near future. Simulation of the surface of Proxima, the journey to understanding Proxima B, began long before JWST was launched. In 2016, scientists ran simulations to predict how JWST would study the surface of this fascinating exoplanet. The purpose of these simulations was to analyze the atmospheric and thermal properties of Proxima B, laying the basis for future observations. At the time, scientists were already wondering if Proxima B had an atmosphere that could support life. Proxima B's unique orbit in Proxima Centauri's habitable zone makes it an excellent candidate for such studies. The planet is hopefully locked, meaning one side always faces the star while the other remains in perpetual darkness. This leads to extreme temperature differences between the day and night side, unless there is an atmosphere to redistribute the heat. Without an atmosphere, it would be hot during the day and freezing cold at night. The atmosphere, on the other hand, would allow for a more even distribution of heat, potentially creating habitable conditions. Analyzing Proxima B's atmosphere, JWST's ability to analyze Proxima B's atmosphere is a major advance in exoplanet research. By studying the light that passes through a planet's atmosphere, scientists can determine its composition and assess its potential to support life. To do this, it is necessary to look for biomarkers, molecules that indicate the presence of biological activity. Water, carbon dioxide, and methane are the most important biomarkers that scientists are looking for. In recent observations, JWST has already detected signs of these biomarkers in other exoplanets, such as 218. The presence of multiple biomarkers increases the likelihood that these distant worlds may harbor life. The potential discovery of ozone, a strong indicator of biological activity, is particularly exciting because it is primarily produced by living organisms on Earth. Although no artificial light has yet been detected from 218b, the presence of biomarkers indicates that it may be an inhabited world with intelligent life in its oceans. Potential to detect plant growth. In addition to detecting artificial light and atmospheric biomarkers, JWST has the potential to detect plant growth on exoplanets. This would involve analyzing specific wavelengths of light reflected by plants, known as VR. Vegetation reg. Plants reflect light in the near-infrared region in a characteristic pattern that can be detected by sensitive instruments such as JWST. Detecting plant growth on exoplanets is a complex task that requires very precise measurements and high-resolution data. Atmospheric disturbances and the signal-to-noise ratio can affect the accuracy of these measurements. But JWST is designed to overcome these challenges, and scientists are constantly improving their techniques. Direct evidence of plant growth would provide strong evidence for life, even if no artificial light or advanced technology is detected. Future telescopes and missions will greatly improve the search for life on exoplanets. The LUVOIR telescope, or Large Ultraviolet Optical Infrared Surveyor, is one such project. This future space telescope aims to study the properties of exoplanet atmospheres even more closely than JWST. Covering a greater number of wavelength ranges, LUVOIR performs the more detailed spectral analyses needed to detect vegetation or biological activity. Another important telescope under development is the HABEX Habitable Exoplanet Imaging Mission. This mission will take the first direct images of Earth-like exoplanets and analyze their atmospheres, with a particular focus on identifying habitable conditions and potential biosignatures. JWST provides critical information in the search for extraterrestrial life. Extremely Large Telescope, ELT. The ELT, which will be commissioned in 2028, will also play an important role in the study of exoplanets. Located in the Atacama Desert in Chile, the ELT is the world's largest optical and near-infrared telescope. Its 39-meter primary mirror allows the detection of weak signals from distant planets and provides a detailed spectral analysis of their atmospheres. The high-resolution capabilities of the ELT make it possible to study the composition of an exoplanet's atmosphere, looking for water, carbon dioxide, methane, and other biomarkers. Using adaptive optics, the ELT can correct for atmospheric distortions, providing sharper images and more accurate data. This allows scientists to look for signs of artificial light or surface structures that indicate advanced civilizations. Differences between JWST and ELT. Though JWST and ELT are designed to study exoplanets, they have a different strength and focus. JWST, primarily an infrared telescope, is located in space and is excellent for observing deep infrared sources and studying the beginning of the universe. The ground-based ELT telescope has a much larger aperture, which provides better resolution in the optical and near-infrared regions. This makes the ELT particularly suitable for studying the atmosphere and surface properties of exoplanets. JWST's location in space allows it to avoid distortions caused by Earth's atmosphere and provide clearer and more detailed infrared observations. In contrast, the ELT benefits from its larger mirror, which can collect more light and resolve better details. Together, these telescopes complement each other and provide a complete picture of distant planets and their potential to support life. LUVOIR and JWST missions. The LUVOIR and JWST missions represent the next generation of space telescopes designed to support the success of JWST and ELT. LUVOIR aims to provide an even more detailed analysis of exoplanet atmospheres using a wider range of wavelengths to detect biomarkers and possible signs of life. Focused on imaging Earth-like exoplanets, JWST provides direct evidence of habitable conditions and potential biosignatures. Both missions will benefit from advances in technology and our growing knowledge of exoplanets. By combining the strengths of multiple telescopes and instruments, scientists can gather a wealth of information about distant worlds, helping to answer the age-old question of whether we are alone in the universe. Quantum communication and the future of extraterrestrial contact detection of artificial light from Proxima B suggests that we may not be alone in the universe. However, contacting extraterrestrial civilizations is a big challenge. Traditional communication methods, such as radio waves, are limited by the great distances between stars. It took more than 4 years for the messages sent to Proxima B to arrive, and another 4 years for the replies. Quantum communication technology holds great promise for overcoming these limitations. Using the principles of quantum entanglement, it may be possible to create instantaneous communication across great distances. Although this technology is still in its infancy, continued research and development could lead to breakthroughs that allow real-time communication with distant civilizations. The role of simulations in exoplanet researcher simulations played a crucial role in preparing the study of Proxima B and other exoplanets. In 2016, scientists used simulations to predict how JWST would study the surface of Proxima B. These simulations helped scientists understand the planet's atmospheric and thermal properties, laying the groundwork for future observations. Simulations allow scientists to explore different scenarios and predict the results of different observations. By modeling the interaction between light and the planet's atmosphere, scientists can determine the best strategies for detecting biomarkers and other signs of life. These simulations are invaluable in the development of new instruments and missions and ensure that we get the most out of our observational capabilities. Implications of finding extraterrestrial life. The discovery of extraterrestrial life would have profound consequences for humanity. This would challenge our understanding of our place in the universe and potentially shape our philosophies, religions, and scientific theories. Proxima B's detection of artificial light indicates that advanced civilizations may exist outside our solar system, raising questions about their culture, technology, and communication capabilities. Contact with an advanced extraterrestrial civilization would be a huge achievement that would open new avenues of scientific and cultural exchange. They could lead to breakthroughs in technology, medicine, and our understanding of the universe. However, this also brings ethical and practical challenges, as we must consider the consequences of interacting with an unknown and potentially very different life form. The importance of interdisciplinary collaboration. The search for extraterrestrial life is a multidisciplinary endeavor involving astronomers, biologists, chemists, physicists, and engineers. Collaboration in these areas is essential in developing the instruments and techniques necessary to detect signs of life on distant planets. The JWST, ELT, LUVOIR, and HABEX missions all represent the culmination of efforts by scientists and engineers around the world. Interdisciplinary collaboration is also crucial in the interpretation of data collected through these tools. For example, understanding the chemical composition of an exoplanet's atmosphere requires knowledge of chemistry and atmospheric science. Knowledge of physics, biology, and optics is required to identify the red edge markings of artificial light or vegetation. Working together, scientists can piece together the complexity of life in the universe. The development of space telescopes was driven by the desire to explore the universe in more detail and answer fundamental questions about our existence. Launched in 1990, the Hubble Space Telescope revolutionized our understanding of space, providing stunning images and valuable information about everything from distant galaxies to the expansion of the universe. JWST builds on Hubble's legacy and offers even greater sensitivity and resolution in the infrared spectrum. Future telescopes like ELT, LUVOIR, and HABEX will continue this development, pushing the limits of what we can observe and analyze. Each new generation of telescopes brings technological advances and a deeper understanding of the universe, allowing us to explore new frontiers and make amazing discoveries. The role of citizen science in exoplanet research. Citizen science has become an important part of exoplanet research, involving the public in the search for distant worlds and possible signs of life. Projects like Planet Hunters, part of the Zooniverse platform, allow amateur astronomers and hobbyists to analyze data from telescopes and help identify potential exoplanets. By engaging the public, these projects not only expand the pool of data analysts, but also increase awareness and interest in astronomy and space exploration. Citizen scientists have made significant contributions to the study of exoplanets, discovering new planets and providing valuable information about their properties. This collaborative approach democratizes science and allows people from all backgrounds to participate in the search for extraterrestrial life. As technology advances, the role of citizen science is likely to grow, providing even more opportunities for public participation in groundbreaking research. Searching for biosignatures beyond Proxima. While the artificial light detection of Proxima B is an important milestone, the search for biosignatures extends to many other exoplanets. Each new discovery increases our understanding of the possibilities of life beyond Earth. The JWST, ELT, LUVOIR, and HABEX missions play a critical role in this ongoing search, using their advanced instruments to detect signs of life on many exoplanets. Biosignatures can take many forms, from the presence of certain molecules in a planet's atmosphere to the detection of surface features indicative of biological activity. By studying different exoplanets, scientists can identify patterns and commonalities that may indicate the presence of life. This comprehensive approach increases the chance of making a definitive discovery and helps build a more complete picture of the possibilities for life in the universe. The importance of education and outreach are essential parts of the search for extraterrestrial life. By sharing the excitement and importance of this research with the public, scientists can inspire the next generation of astronomers, engineers, and scientists. Collaborative programs, educational materials, and public discussions help explain the science behind exoplanet research and make it accessible to people of all ages. Educational initiatives can also emphasize the importance of critical thinking and the scientific method. By engaging with the public and fostering curiosity, scientists can encourage more people to pursue careers in STEM fields and advance our understanding of the universe. As we continue to explore space, education and outreach play a key role in ensuring that the knowledge and benefits of this exploration are widely shared. Ethical implications of the discovery of extraterrestrial life. The discovery of extraterrestrial life raises many ethical questions and considerations. How should we respond to the discovery of intelligent life? What protocols should be used to communicate with an alien civilization? These issues require careful consideration and the development of international guidelines and policies. One important ethical issue is the possible consequences of contact with extraterrestrial life on human society. The discovery of advanced civilizations can challenge our cultural and religious beliefs and lead to significant social changes. It is important to think about how to manage these influences in a way that promotes understanding and minimizes conflict. Another consideration is the potential risk of contamination, both biological and cultural. Contact with alien life can cause new diseases or disrupt existing ecosystems. Also, the adoption of human culture and technology may have unintended consequences for an alien civilization. Developing protocols to address these risks is important to ensure that the search for extraterrestrial life is conducted responsibly. The role of international cooperation in the search for extraterrestrial life is a global effort that requires the cooperation of countries and space agencies. JWST was developed and operated by NASA, the European Space Agency, ESA, and the Canadian Space Agency, CASA. Similarly, future missions such as LUVOIR and HABEX will rely on international partnerships to achieve their goals. International cooperation allows pooling of resources and expertise, enabling more ambitious projects than any one country could undertake alone. It also promotes a sense of common purpose and humanity as people around the world work together to explore space. By continuing to build and strengthen these partnerships, we can ensure that the search for extraterrestrial life remains a collaborative and inclusive endeavor. The future of exoplanet research is bright, with many exciting developments on the horizon. Our understanding of telescope technology, data techniques, and planetary systems continues to advance in this field. Next, generation telescopes such as ELT, LUVOIR, and HABEX will provide unprecedented insights into the properties of exoplanets and their potential to support life. As our observational skills improve, we will be able to take a closer look at smaller, Earth-like exoplanets. This increases the likelihood of finding biomarkers and the eventual discovery of extraterrestrial life. At the same time, ongoing research into the origin and evolution of life on Earth provides valuable context for understanding the possibility of life on other planets. Human capabilities for exoplanet exploration. While the current focus of the discovery of extraterrestrial life is remote sensing, the future may include the possibility of human exploration of exoplanets. Advances in space travel technologies, such as faster propulsion systems and long-term life support, may one day allow humans to travel to distant star systems and explore their planets firsthand. Human exploration of exoplanets presents significant challenges, including vast distances and the need for sustainable life support systems. However, the potential rewards are huge, providing the opportunity to directly explore alien ecosystems and potentially interact with intelligent civilizations. As our technology and understanding of space travel continues to advance, the dream of exploring exoplanets may become a reality. This discovery suggests the existence of advanced technology and possibly intelligent civilizations outside our solar system. JWST, along with future telescopes such as ELT, LUVOIR, and HABEX, will continue to push the boundaries of our understanding by providing detailed analyses of exoplanet atmospheres and surface conditions. Looking to the future, a combination of technological innovation, international collaboration, and interdisciplinary research will drive this exciting field forward. The search for extraterrestrial life not only addresses fundamental questions about our place in the universe, but also has the potential to unite humanity in a common pursuit of knowledge. Whether through remote sensing or future human exploration, the journey to find extraterrestrial life is just beginning, and the possibilities are truly limitless.